Thank you very much. I'm very glad to be here. And first, let me introduce myself briefly. My name is Nikita, and I work at MadeSafe. That's a company that develops a peer-to-peer network. And so my day job is kind of related to the topic of my today's talk. And today I want to talk to you about WebRTC. And for those who don't know, it's an HTML5 technology that's commonly used to transfer video and voice data. Google Hangouts uses it, as well as many other tools that you might have used to talk to other people directly in your browser. It's been available in most of the major browsers for a while, since at least year 2012, I guess, on both desktop and mobile platforms. But actually, WebRTC is capable of much more than simply transferring media. And in fact, in my opinion, WebRTC is able to spark a new decentralization revolution and help in building a new internet. So my goal today is not to teach you about all the intricate details of this technology, but to inspire you to take action and help to bring that revolution closer. Oops, sec. But there is a reasonable question that you might have. Why do we need that revolution at all? Do we need a new web? Like the current one works quite perfectly now, right? Well, in my opinion, it does, but at the same time, the web and the internet were created a long, long time ago, and on the fundamental level, they're a little bit flawed, because the internet was originally conceived and created as a completely decentralized network that no single authority can control. And the web, as well, was thought of as kind of a cyberspace where every human being is not in control of any government or any corporation, and that they have complete freedom to say what they think and what they want. And the web was a place without any censorship. However, lately, this situation has changed drastically. Nowadays, the web is largely dependent on big corporations that run our infrastructure, like giant data centers. And they provide many useful services, like email, for example. It wasn't always like that, though. At first, people set up and run their own email servers and control their own communications. This approach was not scalable, though. So a natural consequence was that a lot of small commercial email providers sprang up. At first, they were small, and if you was there at the early days of the web, you might remember that it was a great feeling to just create your account and get access to whole 10 to 15 megabytes of your own inbox space. But then something has changed. The more people started to use the internet, the more our services consolidated around just a few of big providers. And the result of that is that now our email usage is confined just to a few giant services, and almost no one runs their own servers. And that's pretty understandable, because it's just too inconvenient and not even strictly required to deal with all that spam all by yourself and handle all those daunting administration tasks. And actually, what happened to email is not unique. We have seen the same process followed for almost anything we use and see on the web. And despite the email protocol itself being decentralized, as many of other original internet protocols, like HTTP, for instance, or FTP, we now have centralized authorities that we depend upon. And previously, we had a concept of home pages which you could serve from your own home computer and put there anything you would like. Now you can kind of still do that, but far more people just create their Facebook or Twitter profiles. And now that what they can write on their profiles is determined not by people themselves, but by the policies of these websites. It's like that we have exchanged our control and our privacy for convenience, and now the large corporations can tell us what we can say on the internet. Now we depend on those centralized services to do many things. We share our files through Dropbox. We share our messages through servers that we can control. We pay with PayPal. You might ask, why is it bad though? Isn't that approach helped to bring millions and now even 1 billion of users to the internet? Well, of course, these services are very nice and there is nothing wrong with them as such. But it's not only about the freedom of speech. It's also about the fact that governments started to snoop into our private data and communications in the name of good things, like protecting children or protecting the world from terrorism. And while these intentions are good, the consequences of allowing other people to read your private data are not. The more power the governments have, the more likely it is that they will use this power in the wrong way. And this is not some kind of theoretical or imaginable problem, because this is our reality already. In countries like Turkey, Russia, and China, where they block hundreds and thousands of websites that they deem inappropriate or bad. But actually, what website you can name as bad? Different cultures have different concepts and understanding of bad and inappropriate. But it's just too easy to use this excuse of a bad website to introduce censorship and silence the political opposition. And we have seen that already even in European countries, like when Spain blocked websites and censored information that was related to the referendum in Catalonia. And of course, we all know about the case of NSA, the American Spatial Agency that collected private data of people from all around the world. So with the power of social networks, which are a very large part of our lives now, governments and corporations can have an unprecedented control over our daily lives, or something like that. Can we change this bleak current state of the web? I believe that we can. We just need to rethink the web from scratch. And that might sound impossible to you at first, but we can create decentralized networks and decentralized web apps that are just as easy to use as any other modern-day web application. And I personally believe that the user experience is even more important than privacy or anything else, because why would you use an app that frustrates you or you don't understand how to use properly? That's one of the reasons why so many privacy-centered applications failed in the past. Like take, for example, P2P and email encryption, which are bulletproof, but at the same time, they're also just too inconvenient for everyday use. And almost no one encrypts their email messages nowadays. So that's also the reason why so many decentralized networks failed as well. And that's why we need to incentivize users to use applications that are aware of these privacy concerns. And I believe that WebRTC can be the answer. Now it's already available in most browsers, and you don't need to install any software or browser plugins for it to work. You just open a web page, and it connects directly to the same users as you without passing data through any intermediary servers. And a lot of people use WebRTC now to transfer media, but not a lot of people know that it can also be used to transfer any arbitrary text or binary data. And in addition to that, despite having web in its name, it's not confined to the web only. And the protocol itself is open, and you can use it from anywhere, not only from a browser. And that's a very powerful idea, because you can create WebRTC applications that work on desktop or Internet of Things devices. All of these devices will be compatible with web browsers, and you can communicate with them directly, skipping any third parties that gather and analyze your private data. WebRTC can also be used to create general-purpose and large-scale peer-to-peer networks, which do not depend on centralized servers or any authorities. And it can also play a significant role in the recent trend of redecentralization, or bringing back the internet to its origins. There already exist a lot of decentralized applications that we use every day. It all started with BitTorrent and Bitcoin, which showed that global scalable peer-to-peer networks are possible. And today, not a small part of the world's internet traffic consists of BitTorrent usage. And this is a very important fact that shows that decentralized apps are not purely like abstract or theoretical, and that they are needed by the people. So WebRTC can serve as a kind of a bridge to existing peer-to-peer networks, and with its help, they can create a lot of new networks as well. On the practical side, the WebRTC API is simple. It's a bit hard when it gets to establishing a connection, as we will see, but for the message passing, it's very similar to the WebSocket API. Just initialize a data channel, which is a data stream between two peers. You set a callback function that will be called each time you get a new message, and then you can send a message yourself. The other side will get it, and the onMessage callback will be triggered. And that's almost all you need to know about exchanging messages in WebRTC. And behind the scenes, the protocol guarantees that your messages will be encrypted. The encryption is defined in the standard, and it is mandatory. You don't need to do anything to set it up. The session encryption keys will be automatically created during the connection initialization step. So our communications are secure, and they can't be tapped by anyone. But most importantly, you have to set up the connection properly first. And to do that, you need to understand the concept of signaling, which is quite a complex topic by itself. But to put it simply, it's a connection stage when peers share their IP addresses and encryption keys with each other, and they do that through some point of exchange that they have agreed upon in advance. That point of exchange can be practically anything, a WebSocket server, an email exchange, or some secure chat. It doesn't matter. Some people might consider it, this point of exchange as a kind of a centralization or a single point of failure, though, and in some sense, it is. But it's not really centralized because the way you do signaling is not defined in the WebRTC standard itself, and it gives you a big extent of freedom in choosing the most efficient way that suits your application best. So it can be compared to DNS. If your DNS server doesn't respond to your request, you can always still get to the server if you know its IP address, right? So having that information, you can bypass some of the centralized parts of the internet infrastructure. And the same thing basically applies to WebRTC. If you know IP addresses of your peers, you can exchange the session information with them directly. And when they get that information, you won't need to deal with any kind of centralized servers anymore. And now that we have learned the basic concepts, we can try to establish a WebRTC connection, which is a bit more complicated than the data channels API. But when you learn it, it becomes rather intuitive. So what you need to know about it is that there are two sides of the handshake process and the connection: the initiator and the recipient. The initiator creates an offer which contains a session encryption key, and in case if you want to stream media, it will also contain the information about media encoding, available codecs, and so on. So when an initiator has created an offer, they need to set it as a local description of the connection, which will tell the browser how it should decode the incoming messages. As a final step, you need to send your offer to the recipient through the signaling channel, which again can be a WebSocket connection or whatever you choose it to be. And on the other end, the party that you want to connect to, the recipient, receives an offer through the signaling channel. And then they follow almost the same exact steps, only this time they will need to set your offer as a remote description instead, which will tell the browser how it should encode the outgoing messages. Then the other end should create an answer which in turn will contain their encryption keys and the session information. They set it as their local description and then send it through the same signaling channel to the initiator party. Finally, when the initiator gets the answer, they just set it as their remote description. And now both parties should have the full information to exchange messages. Both should know each other's encryption keys. And now we can forget about the signaling server for now. But not really, because you also have to care about exchanging not only the encryption keys between the two parties, but also, and most importantly and most crucially, their connection information. That is, you need to know an IP address of the other side to connect to them directly. And there is a caveat with the direct connections, because in the real world, most likely you will have to deal with NATs, or network address translators. Most people deal with NATs in the form of routers, which translate addresses from your local network to the real internet IP addresses. And in fact, it's not unusual to see a case when behind a single global IP address, there are several hundred devices in the local network area. And we need NATs because the IP version for address space is limited with 4 billion addresses, and we have a lot more devices in the world now. And because of NATs, direct connections to peers in peer-to-peer networks become complicated. You have to bypass these NATs with one of the NAT traversal techniques. And this task is a bit complicated because of the fact that there is no single standard way for NATs. There's no single standard way to structure NATs, but there are many of them. Full column, port-restricted, symmetric NATs, and even more non-conventional configurations. And each type requires its own approach to bypass it. But the good thing is, these techniques are well known. And in the simplest case, it works in a pretty straightforward way. You just send a request to some external address, and NAT opens a port so that the external party could send you a response. Now, if you know that port number, you can just reuse it and send it back to your peer along with your public IP address. And now that the NAT knows that any data that gets to this port should be forwarded to you, you can communicate with your peers directly. And WebRTC takes care about all of that for us, so we don't need to be involved in that at all. All that's required from us is to collect our public IP address and a port and transfer them to our peer through the signaling channel. But you have to discover your own IP addresses and port in the first place. Like most often, you would do that through STUN. STUN is a basic protocol that allows you to get your own IP address by sending a request to a STUN server, which basically acts as a kind of a mirror. You send your request from your local network, and the STUN server sees your translated address and the port and sends them back to you. And then you just need to broadcast them through the signaling channel. It is the simplest case through because sometimes for various reasons your peers can't connect to you directly. Like in the case when you're behind a symmetric NAT, which will have a random port numbers assigned for each connections. But this problem can be solved as well with the other technique to bypass NATs. It is called turn. But turn is a kind of last resort because it basically works as a proxy server relaying traffic between peers. Obviously, turn is a costly solution, and you can't find a turn server in the wild, as opposed to STUN, which is commonly provided by many servers. There is even a Google STUN server, so you can find a lot of them. But luckily, you won't need to resort to turn in many cases because symmetric NATs are not that common. So to exchange the connection information, there exists another special protocol that WebRTC uses, which is called ICE. ICE helps to discover all candidates, or IP addresses and port pairs, by combining various NAT traversal techniques. It also collects your local IP addresses, so if your peers are on the local network, you won't even need to go through the internet to connect to them. So with ICE, we gather all candidates that we can find and send them to the other party, which tries to use them all at once asynchronously, meaning they will try to connect to us through all available means, and finally, hopefully, resulting in a successful connection. And the WebRTC implementation of this protocol allows us to concentrate on the application side because all that it requires from us is that we need to provide the STUN and turn server addresses. And then We set a callback function and send each collected candidate through the signaling channel. And on the other end, our peer listens on the signaling channel for incoming ICE candidates and tries to use them as soon as they come. In the real world, however, it's a bit more nuanced, but basically, that's all we need to know about setting up a basic WebRTC connection. However, what we have seen so far was just the most simple possible topology. We set up a connection between just two peers, which can be useful, of course, but usually you imagine peer-to-peer networks as having more actors. Like if you have just two peers in your network, you can just have a chat or exchange files with other person, but it's not that useful. And if you want to connect more peers to your network, that's where it starts to get more complicated. With multiple peers, there are many ways to structure the P2P network. You can just connect all peers to each other, but it won't be the most efficient way to do that. Because if you transfer large files or voice or video data, you will have to duplicate this traffic for each connection. And it might work for a small connection with 4 or 5 peers, but it won't scale to hundreds and even tens of peers. It will just require too much bandwidth and processing power. There's an answer to that problem too. You can choose one or more peers that have the most processing power and make them serve all other peers, relaying traffic and multiplexing requests. This is called star topology, and it is pretty efficient. It is also secure because the serving peers still won't have access to the session encryption keys. But at the same time, your network will start to rely on a single point of failure, and it will depend on a good behavior of just a couple of nodes. So it will be kind of centralized again. It is efficient for transferring video and voice data, though, and many such applications use it, like Google Hangouts, for instance. But there are also many more alternative ways of structuring P2P networks. This topic is a bit out of scope of this talk, unfortunately, because it will be easy to spend at least 30 minutes more to talk just about one of the algorithms. So we can just mention that one of the prominent ones is the distributed hash table, which has many different implementations. It is also used by the BitTorrent network, for example. And many of us have used BitTorrent at least once. And this protocol also has an interesting history because at first it depended on centralized trackers to find the connection info and IP addresses of peers that serve files that you are searching for. This has an obvious disadvantage of trackers being that authorities are able to log the trackers, and then you can't find the connection information, and then you can't download the file. So now BitTorrent supports the distributed hash table algorithm. So all you need to do is just find a single peer to bootstrap from, because requests for files can be propagated throughout the network with several hops, instead of relying on a single point of failure. And the process of the initial connection to the network is now usually done just by contacting a well-known node. And then it can continue to work in a decentralized way because each node knows about its neighbors or those nodes who contacted them. So if you know at least a single IP address of a BitTorrent node, you can join the full network. And now an interesting question. What will happen if we combine BitTorrent with WebRTC? We get WebTorrent, which is a BitTorrent protocol implementation for JavaScript, which can work in browsers as well as on the server side. And although it can't communicate with BitTorrent peers directly from a browser because of incompatible network protocols, it still allows us to do a lot of interesting things. And it simplifies the interaction with the WebRTC protocol a lot. We don't need to care about signaling and all that stuff. All we have to do is to serve a file to the network, and this file will be automatically converted into a torrent and announced on the tracker behind the scenes. And WebTorrent has a pretty straightforward API. You can serve basically anything as a file. It can be a blob, a JSON object, or even a JavaScript string. Other peers, knowing the torrent hash, can download this file and set it further. And files are generally not limited to Linux distribution archives or whatever you usually download from torrents. Any information can be represented as an abstract file. So WebTorrent can be used for much more than just file sharing. For instance, we can build a distributed GitHub quite easily because Git extensively uses and relies on hashes for its internal implementation. So it will be very straightforward to serve the Git packed objects through torrents. There is even a proof of concept project called BitTorrent that already does just that. And we can reuse the same protocol to serve web pages or static content and make a kind of distributed content delivery network so that each visitor of your website will serve the website's content to each other visitor. And you can find many more applications of the BitTorrent protocol. But still, despite of being very promising, WebRTC is an immature technology. It still needs to come a long way to support large-scale networks that can transform the current centralized state of the web. It's not perfect and has many limitations. The browser support is not perfect, for instance, and current modern web browsers, such as Chrome or Firefox, still limit the number of connections that you can establish. And because of this limitation and because of the handshake overhead, it's practically impossible to build DHT networks which make the WebTorrent implementation dependent on the centralized trackers for now. And in addition to that, WebRTC doesn't allow us to use raw sockets, so you can't connect to the existing networks directly. You'll have to go through proxies. And another important issue is that browser sessions are usually short-lived. When you close your tab, you will lose all connections. And the next time, you will have to go through the costly signaling and the connection initiation process again. This problem can be theoretically alleviated by allowing to run WebRTC sessions in service workers, so that even if you close a tab with a WebRTC connection, you will still maintain your connection to the network of peers. But it's kind of not possible for now, and it's currently being developed. Another possible solution to the problem of short-lived sessions is hybrid servers. Because as I said earlier, the WebRTC implementation is not limited to browsers, so we can integrate the WebRTC protocol support into the existing peer-to-peer networks, and they can act as kind of intermediary servers. Still, while there is a lot of problems to overcome, WebRTC is very useful today, and I'm hoping to see many new projects that use this protocol. But P2P networks in general have their own set of problems to solve, because these networks are trustless. It's hard to solve the problem of malicious peers, for instance, which can spam your network or misbehave in order to gain some advantages. And if we store content in multiple nodes, we step into the territory of distributed systems, which are very complex, because we'll have to deal with data consistency and churn. Because imagine that all nodes that store some file on the network leave all at once. Effectively, this file will be lost. And it's completely fine if that file has no value to you, like if it's another of Justin Bieber's songs or whatever. But imagine if that file was your Bitcoin wallet. You certainly wouldn't want to lose it. That's why, for redundancy, we have to make sure to have enough copies of the same file distributed over many nodes. And it is definitely not an easy task to coordinate nodes which don't trust each other. So if we are talking about a long-lasting global-scale network, we need to make sure that peers in these networks are incentivized to stay. And in my opinion, the economy of P2P networks is even more important than their algorithms. Because not a lot of people would want to share their resources if there is no reward for them. Bitcoin kind of solved this problem by giving some coins to mining nodes, but it's tricky, because some strategies can lead to centralization all over again. We have seen that on the same example of Bitcoin, where mining is now largely consolidated around just a few large pools. And remember that the internet itself originally was started as a distributed network too. But the question of who provides the resources and who serves the web pages leads us to the modern days of giant centralized data centers and mega corporations. So this is an open question, and we ought to look for an answer. Because I think answering this question will be very beneficial for all of us. We can do a lot with WebRTC, and we can transform the current internet. We can bring existing P2P networks, such as Tor, to web by porting them to WebAssembly and adding the WebRTC protocol support. We can build new P2P networks that won't depend on the will of governments and greedy corporations. These networks can be used to get back the control over data to the people because they're more secure and resilient. And the application of WebRTC will be especially important in the area of Internet of Things. As we can see that medical devices, self-driving cars, smart homes, and critical infrastructure already depends on the internet, which is by and large controlled by a few big players now. And I strongly believe that it's not right to give these mega corporations and governments even more power and control over our data and consequently over our daily lives. So you can find me on Twitter, and there is a link to a page listing some useful resources related to this talk. And thanks a lot for your attention.